Okay, so as you'll recall, we've been working in this basic framework where there are two sectors, a final goods sector producing this homogeneous output, and an R&D sector producing new kinds of capital and or labor augmenting technology. Okay, the A and the B. Let's call these the Y and the A sectors. And let's say production is homothetic in both. So we can define this substitution parameter, rho y and rho a, just as a function of the ratios of the two inputs, okay, effective capital to effective labor. That is, the substitutability won't depend on the absolute quantities of capital and labor, just on the ratio between them. Now, as long as these substitution parameters are negative, so the factors are gross complements in each sector, all that we really care about for growth purposes is the scarcer factor. We can ignore the plentiful one because growth will just be constrained by the scarcer one. And as we also kind of discussed, the conventional assumptions are that the factors are gross complements in both sectors, okay? So the substitution parameter is not just less than zero, but bounded below zero. So it doesn't like asymptotically approach the Cobb-Douglas case of zero or anything like that. Yeah, sufficient saving is keeping effective labor as the scarce factor. Capital is plentiful. Today and tomorrow, we'll maintain those assumptions, and we'll just look at how AI might incrementally increase labor augmenting technology, more or less. I mean, we'll work out the details, but basically it could just function like past technologies. We'll see how that could happen in the context of a task-based model. Then on Wednesday, we'll maintain the assumption that you need people to do R&D, but consider the implications of gross substitutability in production. Okay. The robots can build whatever we want to consume and all the capital goods we need to produce in the future. Then on Thursday, we'll suppose the opposite. What if people are needed to produce, but AI can do R&D without human help? And then finally on Friday, we'll consider what happens under true full automation, true like AGI and full robotics across both sectors. So to start with, suppose that output is produced via a Cobb-Douglas combination of tasks. So yi will be the quantity of task I produced. And to start, let's say the tasks are discrete. So you've got n discrete tasks here. You've got total factor productivity. That's a well-defined quantity because output is Cobb-Douglas here. And, it's constant returns to scale as usual. So the sum of the exponents equals 1. And each task can be assigned some capital and or some labor subject to our constraints, the stocks of each factor available. And we'll say that labor is fixed. Capital can accumulate. Other things can change, but labor is fixed. For some threshold task T, we'll say that tasks with lower indexes are automatable, meaning they can be performed by capital or labor. But tasks indexed T or higher can only be performed by labor. Okay, so the quantity of task I performed, this yi, is just the sum of the capital and labor applied to it if the task is automatable. But if the task is not automatable, the output of that task just equals the amount of labor assigned to it. There's no sense applying any capital to it, but if you did, it wouldn't do anything because this is not a task the capital can do. Now, essentially, without loss of generality, we can imagine that the tasks are cut up finely enough that each one has the same share. So, suppose that the share on task I is double that for all the other tasks j, then we can just split that task I in two and say all the resources that are that we think of as being allocated to task I are just splitting their time evenly between those subtasks I1 and I2. Yeah, output's going to be unchanged. And there's a little subtlety here to the fact that, um, you know, given that you're applying, um, half as much of your inputs to the I1 and the I2, and then you're raising that one half to this sum of the powers, which is the AI, the A sub I. You're going to need a new kind of expression for TFP. But I mean, you can work through the algebra if you want. But basically, the point is you can just think of all the tasks as having the same share, and you can cut them up if they're not. Now consider an analogous model. The reason for kind of doing this exercise is because I think it's easier to grasp what we mean by the tasks being discrete when you have, like a finite number of them, and you're just sort of multiplying them together like that. But we want to cut them up finely enough that we can basically integrate across them instead of summing. All right, so let's say you've got a continuum of tasks of measure 1. And let's take the log of the production function. So this is just, in the discrete task case, it will look exactly like this, except you'd be summing from 1 to n instead of iterating from 0 to 1 here, right? And then you can exponentiate both sides to get an expression for output itself again. So output is total factor productivity times e to the integral of log task-specific output. Now, because the tasks are symmetric and because the contribution of each one to output is strictly concave, you're going to want to equalize your allocation of inputs across tasks to the extent that you can. Okay? So if you've got more capital per automatable task than you have labor per non-automatable task, it'll be optimal for all of the automatable tasks to be fully automated. You're not going to want to use any of your precious labor on the things that capital can do. Because even if you only use the labor on the 1 minus t things that it can't do, you still don't have as much as you'd like relative to the capital. You wish you could, well, if this inequality is strict anyway, you wish you could use some of the capital on the non-automatable tasks. You're not going to make matters worse by putting labor the other way. So let's call this inequality the automation condition. If it holds, as I was just sort of gesturing at, you're going to spread your capital evenly across the automatable tasks. So for each I less than t, you're going to use the same amount of capital. It'll just be k over t. And likewise, you'll spread the labor evenly over the rest. For some more intuition, you can think of capital as dirt and labor as water. Say they're sitting in a tub 1 unit wide, representing the unit continuum of tasks. If the automation condition is not met, then you have less capital per automatable task than you have labor per non-automatable task. So you can equalize the production of each by letting the water spill over the land, right? If the automation condition is met with strict inequality, this is case 3 over here, then the dirt line will be above the water line. And output, or really output per unit of TFP, is going to lie in between. And this just kind of follows from constant returns to scale. Output per unit of TFP equals this original level, in this case. And it would be like if capital and labor were both increased by 20% or something, output would also be increased by 20%. But here we're just increasing one of the two factors by the 20%. So output will rise by some intermediate amount. Okay, now we'll move from thinking about tasks to getting a reduced form expression for output with tasks just as a sort of micro foundation. So we've got our production function and we've got our quantities of inputs for each task. Substituting the latter into the former, you see that output will be P, that's TFP, times e to the integral from 0 to 1, now that's got two parts here, of log task input. And since, this is just a constant, this doesn't depend on I, that's just going to be, e to the t times log k over t plus 1 minus t times log L over 1 minus t. And, e to the log something is just something. So that'll be this here, k over t to the t, L over 1 minus t to the 1 minus t. Now, taking t as a constant, we can roll these expressions in the denominators into our productivity term. We can call this modified productivity term p tilde. And if we do that, then we're just back to a familiar Cobb-Douglas expression here, right? Just holding t fixed, output is Cobb-Douglas in capital and labor, but the exponent on capital is the fraction of shares, fraction of share weighted tasks that are automated. So just to sort of hammer home how this is a standard Cobb-Douglas model, suppose that TFP grows at some rate, GP, right? Well, holding T fixed, P tilde will also be growing at rate GP, right? Because T, this coefficient on the P will be constant. Or if you like, you can roll the technology term under the 1 minus T exponent so that it augments the L rather than the whole function. I think, we saw this yesterday. And rewrite our production function, and we get a growth rate of labor augmenting technology. So output will grow at, the rate of labor augmenting technology as usual. And that'll be proportional to the rate of TFP growth. Different ways to get to the same expression. Now, the thing is, if we increase automatability, okay, if our technological development takes the form of allowing capital to do new tasks rather than this sort of, abstracted thing, this just an increase in this efficiency term on the outside of the function. If we do what we have been doing for hundreds of years and let capital do more things, if we raise t to some t prime that's greater than the original t, then as long as the automation condition is maintained, so we're still kind of, output still takes this form, what's going to happen? Well, output will increase immediately because we now have a more efficient resource allocation across the tasks. The dirt can spread out more into the sea as you want it to. And that's intuitive enough. We create more kinds of automation technology that'll increase output. But it will raise GB. And so it'll raise the steady state growth rate of output. Okay? Yeah, again, you can see this one way or the other up here, but like when you increase the exponent on capital, just maintaining the growth rate of P, you get a faster growth rate of Y. And this is basically because Y is growing for two reasons: the growth rate of TFP and the feedback loop whereby more output means more capital to some extent means more output. And that feedback loop is stronger when the exponent on capital is higher. So just same rate of TFP growth, but you increase the growth rate of output. And you also raise the capital share, right? Because that's just going to equal the exponent on capital. Briefly, just to make sure our intuitions are solid, note that naively you might think that if t equaled 1, if we got to full automation, we'd get not just like really fast growth, but infinite growth. Because our expression here is that gy is 1 over 1 minus t times gp. So if you've got some exogenous gp, 1% a year or whatever, well, 1 over 0, and this is going to be infinite. The reason that's not right is that unless you also had infinite capital, which you won't, that would take infinite time to accrue, the automation condition can't hold if t equals 1, right? The water line, if we suddenly sent t really close to 1, we'd have this little pinstripe of water going to the moon. That would just have to spill over the land. Okay, so the condition would actually break, and you wouldn't get infinite growth. What actually happens under full automation here is that y will basically be ak. Strictly, it'll be TFP times k plus L. But basically, you can think of it as an AK model, right? L is fixed, k is growing with output, and so it'll grow at rate SP minus D, just kind of ignoring the L. It'll grow at this rate. We've seen this formula before, and given positive GP, this growth rate is going to go to infinity, but it won't go to infinity instantaneously, right? You'll have robots building robots, and how many robots a robot can build in a year, that's going to be P, that's rising. So you have 1 robot, and then 2, and then more than 4, 6, you have then, 24. But the ever faster growth rate never actually gets to infinity. Okay. So the model of that previous section, I think, is helpful for introducing the idea of a task-based model as simply as possible, but it has all sorts of undesirable implications. So just for starters, it implies that we should observe Cobb-Douglas production in aggregate, right? And as noted before, I think in practice we typically find gross complementarity. And certainly intuitively, I would expect gross complementarity. Right. Relatedly, the model implies that advances in automation, that's increases in T, should not only raise output instantaneously, but raise the growth rate forever after, as well as the capital share. And this hasn't happened, right? We've had great advances in automation since the Industrial Revolution, but the Kaldor facts have been maintained. And this Aghion et al. Model from 2019, I think, does a great job of very simply, just with one atom more complexity, showing us what we should expect automation to do if the tasks are gross complements. And it turns out that both these facts are maintained in a really nice way. So to see that, let's modify the model of the last section so that output is it's still CES, but now it's a gross complements combination of this continuum of tasks. We still have symmetry across the tasks, and it's still the case that each task offers diminishing returns to the creation of output. We still got this concavity. So it's still the case that while the automation condition holds, we'll want to spread capital and labor evenly across those two ranges. So we can still substitute k over t in for yi for the tasks I less than t, and similarly for the tasks greater than or equal to t. And as you can see pretty straightforwardly from expression 5, that'll reduce to this expression for output, right? You've just got this constant thing, k over t, that you're multiplying. You're integrating from 0 to t for the capital bit. But what you're integrating is just the constant. There should be a di here. Sorry about that. And So you've got T times the K over T to the rho here. Likewise for the labor bit, and that's all to the 1 over rho. And writing, splitting this like T to the 1 minus rho term into some little a and some big A that you put under the rho, and doing something similar for the 1 minus T, we're back to our standard reduced form CES production function. How you split the T to the 1 minus rho into the little a and the big A, it isn't going to matter here. For some intuition, since we're saying that rho is negative, you can think of an assembly line where output is bottlenecked by the least performed task. Now, that'll only literally be exactly right if rho is negative infinity, right? Then you've got a Leontief production function where output's just the minimum of all the tasks. Here, increasing some tasks that aren't the minimum will still increase output, but just up to some kind of finite ceiling. But basically, you're bottlenecked by the least performed task. So what's going on here? Increasing T might seem like a way of augmenting capital, right? You're teaching capital new tricks, not labor. But recall, however we decided to split our expression into the A, the big A and the little A is going to be proportional to T to the 1 minus rho over rho, and B will be proportional to 1 minus T to the 1 minus rho over rho, right? You've got, T to the 1 minus rho, and then you're dividing by rho to get your big A under the rho here. Yeah, that's what we saw here. And so as T rises from 0 to 1, B, labor augmenting technology, is going to rise from a minimum of this thing here, doesn't really matter, to infinity. As T is going to 0, as 1 minus T is going to 0, we're raising something really small to a negative power, right? Because rho is negative, so we've got a positive numerator over a negative denominator. So we're raising something really small to a negative power. That's shooting to infinity. And by the same logic, T going to 1, that's going to cause capital augmenting technology to fall. It'll fall to this little a to the negative 1 over rho. So technological progress here is not only labor augmenting, but actually capital depleting. In particular, just to tie them together, let's say that you've got a constant negative growth rate of that 1 minus T. So every period of time, we are figuring out how to automate some fraction of the remaining tasks. It's like every generation we automate half the remaining tasks on the assembly line or something like that. Then, as you can see, GB will just be the negative of, GB will just be 1 minus rho over rho times this growth rate of 1 minus T. But both of these things will be negative. G1 minus T is negative, and this exponent is negative, as discussed before. So B is growing at a constant exponential rate, and yeah, growing without bound. To maintain the automation condition, what we'll need is precisely the sufficient saving condition from the last lecture yesterday. This is when growth is constrained by a lack of labor augmenting technology rather than a lack of capital accumulation. So for intuition, what's happening is every time we have that set of non-automatable tasks, we need half as much labor to produce the same quantity as we needed before, right? Like we could just dispense with half of the water. but we're going to need slightly more capital. Okay. So that's a sense in which B is doubling and A is falling, but A is only falling a little bit. And in the limit, A is not falling at all. The capital share here will rise from 0, which it is when T is 0, and so A is infinite, right? Remember the formula. When T is 0, A is infinite. The capital share will fall from 0 to this constant, which will, be less than 1. And what's going on basically is that the gap between the land and the water is staying proportionally constant as both grow. So every period we say have the set of tasks not yet automated. That basically lets us double output with the same amount of labor. I mean, in this case, doubling the water line would spill over the land. So let's say we decrease 1 minus t by like 1%. That means we increase the level of the bottlenecking tasks by about 1%. And that'll mean we get about 1% more output, which we can then, use to increase capital in the next period by 1%. And so the process continues and both things grow in proportion. So the marginal product of raising the water line and the land line will be the same. But when you've say halved the water bit, you're doubling the contribution of each drop of water to the water line. It raised it by like 2 millimeters now instead of 1. So wages are growing along with output, and the labor share is staying constant. And the capital share is asymptotically constant because this effect that we're seeing with the water, where you need less and less water to raise the water line by a given amount, is not true of the capital, right? Asymptotically, capital just occupies the whole tub. So what can we take away from this model? I think one thing is just that, as with the animation example of the first lecture yesterday, processes can look different from labor augmenting technology under the hood, but still amount to growth in labor augmenting technology. Right? We can automate some of the tasks involved in animation, and that's basically equivalent to GB. Another takeaway I think is kind of interesting is the illustration that you can have a slightly rising capital share over time alongside an increase in the effective capital to labor ratio without positing that historically we've had growth substitutability between capital and labor. Like that would be true if there were no capital depleting technology. But here you've got this thing that's been causing the capital share to rise a bit, which is basically this functionally labor capital depleting technology process. And finally, the takeaway is that to really break the historical trend of the Kaldor facts, exponential growth, constant labor share, to really break that, you can break it in a small way by just speeding up the rate at which we're automating tasks or something like that. But to break out of the exponential regime altogether and to get to something like an AK world, you have to either really change somehow like how the tasks are combining so that they become at least weekly gross substitutes, or you have to automate every single task. Now that's not exactly true. I'll discuss a caveat in the next section. but it's more or less true. Um, so it's kind of interesting. You can think, oh man, we're like automating all these tasks and we're really getting close to the finish line. But as long as we approach it like Zeno, we can maintain the Caldor facts forever. So as we saw, we can asymptotically maintain the Caldor facts even as the share of automatable tasks is approaching 100%. And as we also noted, at 100%, you get an AK economy. So given sufficient saving, the growth rate is going to rise and the labor share will fall to zero, even if A is fixed, right? Because if we have sufficient saving, what that means is that capital accumulation was not the bottleneck before. So once you kind of relieve the bottleneck of needing to, automate more and more of the tasks, the growth rate will jump up to the capital constrained growth rate. So that SA minus D thing. If A does rise, the growth rate will rise without bound. That'll be an even bigger break from the past. So we get these breaks. And this raises a question of whether there is a sort of qualitative shift in this model at t equals 1. And as I was saying before, not exactly. The shift to an economy functionally looking like an AK economy happens when the automation condition holds with equality. That is, when the land line equals the water line. That kind of makes sense because once you're past that point, capital and labor are perfect substitutes on the margin. You can drop a bit of dirt into the ocean, and yeah, it's got to land on the left. But that's raising the water line, just like just like a bit more water is. And so even at a saving rate of 100%, oh, I shouldn't have said and so. Even at a savings rate of 100%, a rapid drop in 1 minus t in proportional terms will have to break the automation condition. I was sort of getting at this before, but like if we suddenly moved in the landline so that you could have a little pinstripe of water shooting up to the moon, if that shift happened quickly enough, there might just be no way for us to accumulate enough capital to actually kind of maintain the automation condition. We could save everything we've got, and it still wouldn't be enough dirt to prevent the water from spilling over the land. So interestingly, when you think about it, this suggests that it might never be profitable to figure out ways to automate all tasks, right? There's going to be no returns to automating work past the candidate threshold task that would maintain the automation condition with equality. So we can have really, really fast growth, but while people are still around, might as well use them, might as well not automate some little sliver of tasks on the right. Okay, so this is sort of a the conditions for explosive, like kind of AK style growth are not quite as strong as full automation. You can have a shrinking set of non-automatable tasks, and if it's shrinking quickly enough, you could still kind of get the same result. But it might have to be shrinking quickly indeed. That said, we've been assuming this whole time that resources are allocated efficiently, right? So like if 1 minus t halves and output doubles every generation, we've been kind of assuming that half the workforce is retraining each generation. And this seems feasible if it's happening at that pace, but under faster automation, people would have to retrain more quickly, right? In particular, to maintain that automation condition holding even with equality, if we have exponentially growing capital augmenting technology, so if let's say the dirt was itself just growing exponentially, even before accounting for savings, the the uh, the rate at which the band of water is shrinking itself has to be growing exponentially, right? So it has to be growing, 2% a year, then 4%, then 8%. And maybe people can only retrain so quickly, right? Maybe having to switch jobs 100 times in a day is completely infeasible. And if that's right, then lack of labor at tasks near one will remain a bottleneck until we reach full automation, right? Because you've got all this, you've got all this extra water that is just, you're not going to be able to use on that little band of tasks. There's just not enough time to retrain, and so output's going to be really bottlenecked in a big way by the few people that were already doing those few things that are now the last bottleneck tasks. So here you get a real discontinuity and a real incentive to develop true AGI and full robotics. So this retraining bottleneck sounds like it could be a really big deal. On the other hand, AI can help with the retraining process too. Maybe right now it would be infeasible to change jobs very quickly, um, but it could get easier over time. And I think you see something of this effect in really lots of domains. I think in a future lecture, Zach will give us a more comprehensive literature review. But my reading is that on balance, what we're usually seeing here is that AI boosts novices more than experts. Um, and in a way, that's kind of like saying it's speeding the retraining process. It's shortening the path from being a newbie in some tasks to being sort of acting like an expert. And you can imagine an extreme case in which we all wear AI-equipped glasses that give us expert advice on what to do each moment. That would be a case of like practically instantaneous retraining. So the real question, I think, is whether any increase in like the real question for whether a retraining bottleneck will bind is whether some increase to the speed of automation outpaces or is outpaced by any possible accompanying increase to the retraining speed. So yeah, last thing on task-based models will just be some notes on the limitations of the simple models we've considered. First, at face value, the models imply that people are doing ever fewer tasks over time. That doesn't really seem to be right. If anything, the opposite. A really simple tweak we can introduce is just to say that we specialize those non-automatable tasks more as we have more and more people doing them. And we have some sort of slight increase in returns to scale, maybe due to that specialization. Um, I, I think on some level, this is probably the right way to think about it. I mean, many people now do narrow versions of what would once have been considered a job like scribe or philosopher or something. Back then that would have been considered less than 1% of tasks, but now a large fraction of the workforce is doing them. There are more complex models that treat new task creation explicitly. Um, Asimoglu and Restrepo's race between man and machine is an interesting model. They have new tasks sort of replacing old tasks. So you have a sort of it's always a unit interval of tasks, but it's sort of shifting to the right over time, as it were. Um, um, yeah, you've got to be careful because if you just introduce new tasks without doing some trick like theirs, where you're also discarding old tasks or whatever, if you just throw in new tasks and the tasks are gross complements, the new tasks will lower output unless you're performing them in large enough volume, right? Because you're introducing new necessities and new ways to bottleneck yourself. Um, and that's important because, the row greater than zero case, the gross substitution case, I think is so unrealistic and would imply that we basically have full automation already, right? Um, yeah, I guess my favorite way of dealing with new tasks would be to allow for variable elasticity of substitution rather than the thing of discarding old tasks. So they're kind of gross substitutes on the margin when they're introduced, but in large quantities They become gross complements. And we'll discuss this a bit more in later lectures. We'll be thinking about new goods rather than new tasks, but the logic will be the same. We won't get into this now because our focus will just be on that qualitative gap between partial and full automation, right? How you can have a lot of partial automation and maintain the Caldor facts, but that they really got to break with full automation. A second limitation of this sort of model is that it assumes that tasks can be automated independently from one another. In practice, though, the fact that someone has to do some task J might make it the case that she has to do task I as well, even if I could be automated in isolation, right? So like a task by task analysis would suggest that task I is automatable, but it's not really in practice because Pamela's got to do it to like prepare herself for task J in some sense. So this point was made to me actually by someone named Pamela, who used this example. She was trying to explain her point over email, and then we had a Zoom call. And so that was the example at hand. Let's say your job consists of two tasks: writing an email to me, answering my question about the limitations of task-based models, or at least this particular limitation. And the other task is to have a Zoom call with me to discuss those limitations in depth. And suppose an LLM can do one, but not two. Then it might be better for Pamela to write the email herself so that she can discuss it well on the call that's coming later. It might take her longer to read and internalize the LLM's points, like what choice of terminology I use and so on. So she knows what's in my head when we have the call. That whole process might take her longer than just writing the email and then discussing it in her own words. One potential way of modeling this, I think, would be to introduce a kind of cross-task learning by doing, where your performance at one task increases your productivity at another one, maybe an especially sort of adjacent one. So, I here would be writing the email, and then Jay is having the Zoom call, right? She's more productive at the Zoom call given that she wrote the email. And in fact, from first principles, I think when you think about it, this is basically what you should expect, right? Because it answers the question of why there are jobs in the first place, right? There's clearly benefits to specialization, right? I don't make my own shirts and so on. I specialize, and given that there are these gains of specialization, why don't we specialize all the way down to the task level instead of doing what we do, which is like transact our labor in these bundles of tasks we call jobs. This could be the reason, right? You actually want to be doing a whole bundle of things because if you split it up too finely, you'd be giving up the learning that you would get from doing those other things. That learning can be really relevant in some cases. So I have some notes on this. I have a sort of simple paper on this here if anyone's interested in thinking about modeling this further. But I think what you should expect this to imply, at least what my modeling of it implies, is that automation will have impacts that come later, but then are more sudden than a simple task model will predict. In fact, not only the impacts of automation, but the actual implementation of automation will be later, but more sudden than a simple model would predict. The simple model evaluates, say, an LLM's abilities task by task, and it says, oh, it can write emails already, but we don't actually use it for writing the emails sometimes. And then once it can write the emails and have the Zoom calls, then suddenly we use it for both. Another implication is that given that there's this cross-task learning, this sort of opens up a new way for advanced AI to yield even more growth, which is that because it can do so many things, or um, while deployed, I guess, gather so much data that can then be used to train future models in a way that's like much more yeah, just much more direct and straightforward than the process by which people can teach each other lessons that they've learned from their own work. This sort of immense cross-task learning can allow for basically bigger jobs, or in the limiting case, one big job, um, that presumably just as right now we value the fact that a person has enough hours in the day to both write emails and take Zoom calls, and so they can be productive by doing both. Um, you know, presumably, it's not like we've just run out of like opportunities for this sort of cross-task efficiency, um, at, at the level of a single person's capacity for work. If one person could work two jobs at once, having that kind of shared context and that shared learning would be valuable. But we have to we have to make do with splitting a task among many people, and that won't happen anymore. Um, yeah, with advanced enough AI. And this is going to be really relevant to the discussion of parallelizing R&D, which we'll get all into in lecture 7. But you kind of see how this works, right? Having a lot of researchers side by side might not make nearly as much progress as having sort of one big researcher that can hold the whole project, the whole state of the frontier in his head. All right, so that's all I'll say about task-based models and automation, at least all I'll say directly. And I'll say a bit about the envelope theorem, just because it turns out to be really useful for applying some of these models in practice. Though, of course, it's relevant to 100 other things as well. I find this easiest to introduce by starting with Roy's identity. Um, I hope I'm not alone in this, but I just find it especially kind of concrete and intuitive a case of the more general theorem. So, if you recall, fixing a budget given an indirect utility function over prices, v of p, and a utility maximizing bundle, this function of prices, you've got this equation, at least under some smoothness conditions, which we won't get into, but under continuous differentiability of utility and so on. So the amount by which your utility falls if the price of a good K goes up a bit equals the quantity of good K you were already buying times your margin utility of wealth. For intuition, suppose the price of good K falls by $1 and you don't change your purchases. Well, this will just save you XK dollars, right? You were buying XK units and you now spend $1 less on each. And so on the margin, oh no, yeah. Okay, so that's the first thing to notice. So if you don't change what you do, you save XK dollars. The second thing to notice is that on the margin, you're indifferent about where to increase your spending, at least, across the goods on which you're already spending a bit. If you're optimizing, at least given the smoothness conditions, you're indifferent about spending a little bit more here or there. And so wherever you spend, you're going to get lambda utils per dollar, right? Lambda is, again, your marginal utility in wealth. You get XK dollars, so you get lambda XK utils. You can frame this in proportional terms. So let's say instead of the price of good K falling by $1, it falls by 1%. Okay, so we'll be multiplying this utility impact by the level that PK is starting at. So we're multiplying both sides by PK. And lambda P here, well, that's your marginal utility in wealth. So that'll be your marginal utility in anything you're buying a positive quantity of divided by its price, because that's what wealth can get you, right? 1 over PK units of good K. So this equals that. And then the PKs cancel. So your utility will rise by how much you like a unit of good K times the quantity that you were buying. Okay, so this is just like if you use all the money that you're saving by PK falling by 1%, if you use all the money you're saving to buy more units of good K, you'll buy XK or like some small amount proportional to XK units. You'll get to buy like proportionally more of good K, and each one will give you this much utility. So to generalize that intuition, I'll just state informally a more general thing that is itself a limited version of the envelope theorem. So suppose we've got our smoothness conditions and we're maximizing some increasing function f of some vectors, x, y, maybe some others. And we're subject to a kind of budget constraint for each vector. So P is kind of like a price vector for the X goods, and that's got to be subject to our G budget. And then we've got one for we've got a Q set of constraints, set of linear constraints on the Y vector, and so on. Then a marginal proportional decrease to the quote unquote price of good I will allow F to rise by as much as if all those savings were spent on good I with no other changes, right? So this is just, this is what we saw before, but with like a U in place of an F. So PI falls by 1%, you can buy 1% more of good I, and F rises by this much per unit. And yeah, this is just kind of for the same reason as before. So that's one thing you can do. And after you've done it, you can make marginal adjustments to get onto your new optimum. But small adjustments would have made no difference before the small change in the price. And given the smoothness conditions, that means that they will make almost no difference after. So for one straightforward application of this envelope theorem, or something a little bit more restricted than the envelope theorem, suppose that output is a composition of n tasks, each of which uses capital and or labor. Okay, now we're allowing things to be more flexible. So the inputs are not perfect substitutes in each task. We just have these kind of flexible little f's. We've still got constant returns to scale and aggregate factors. And you've got these sort of quasi budgets, which are the labor stock and the capital stock. And you buy or allocate capital and labor services across the tasks, subject to the constraints. Now, suppose first that each task is itself composed of a bunch of subtasks, and second, that we're near that asymptotic limit from the model earlier. So automating a subtask is basically the same as increasing labor augmenting technology in that task. So after automating a subtask of task 1 here, we'll say that that's like increasing the labor augmenting technology term by some small amount, say, multiplying it by 1.01. We used to have an implicit 1 here, and now we've got a 1.01. How much will this increase output? This is the real problem, mind you, right? So an increase to B is a relaxation of the constraint, because B is sort of 1 over the price of labor on good I. And just like by the kind of quasi price, right? Yeah, if B is 1% higher, then if you allocate the same labor to task 1 as before, you get 1% more labor services on task 1. And yeah, this is a real problem. And this sort of background story about the tasks is just a kind of relevant application, but it's, this part will only hold exactly in the limit, where we're kind of, we've already automated almost 100% of the subtasks or whatever. So we've got no capital depleting technology or anything. But whether or not this story holds, the second part here will just be exact by the envelope theorem. And what'll happen is that, well, we've kind of lowered the price of labor services in task 1 by a bit. And so output will rise by that little bit, by that 1%, times the marginal product of labor on task 1 times the quantity of labor that was already being used on task 1. So this second term here, this df over dli times df dl1 times l1, that's the wage bill that you had been spending on task 1. And if we just keep the labor allocation the same, we're effectively like saving that 1% of the wage bill. And then what we do with the kind of the labor that we can save doesn't matter, right? Because we were optimizing. So we can just say, well, what if we just kind of keep it on task 1? And so, yeah, output will rise by that 1% times that savings. Okay. This is basically what Acemoglu's famous paper, The Simple Macroeconomics of AI, does. We'll cover this tomorrow, but the upshot is he takes various estimates of the proportional increase in labor augmenting technology by task, like how much time savings AI seems like it'll allow for by like automating subtasks or whatever, and then uses wage bills by occupation to estimate the increase in output that LLMs should be expected to produce. Okay, so that's one application. A similar application is called Halton's theorem. So recall that TFP growth is the share-weighted average of the growth rates of capital and labor augmenting technology. Right, and that this is defined even if like TFP is not well defined. Well, likewise, given the kind of general task-based model that we've been using on the previous slide, we can say that TFP growth on task I is the share-weighted average of capital and labor augmenting technology levels within task I, where the weightings are the capital share in task I, right? Or industry I, or like whatever these things represent. So like the fraction of total expenses there that go to capital. So this is just a definition. Okay, this is what we'll call TFP growth on task I. Now, we can ask, let's say we've got TFP growth of 1% on task I. How much will that increase output? Does it matter whether that TFP growth came from the AI or the BI? And the answer is that given perfect competition, it doesn't matter. And you can see this with some algebra, but I think the logic's pretty straightforward. It's just, if technology changes in such a way that you can sort of save 1% of your, of your expenses on task I to get the same like output of task I, output will increase by as much as if you just pour all those savings back into task I. Yeah. So we have this formula, just another, version of the same formula we've been seeing. It's typically presented in elasticity terms. So you can divide both sides by output and say that the proportional increase in output um, will be the proportional increase in a task's total factor productivity times its Domar weight, where its Domar weight will just be this term here divided by y. So it's like the bill that's being spent on task I or industry I or whatever as a fraction of output. Okay, fraction of like total um, spending on final goods. Note that there is no need for the Domar weights to sum to 1, and this is because many dollars might be spent on intermediate goods per dollar of final output. But that's fine. You can just kind of think through the envelope reasoning. Let's say we've got like these long supply chains, and for every dollar of final output, there's many dollars spent every year on tools that are used to make output that are used to make tools that are used to make tools that are used to make tools to make output. Let's say one of those tools is hammers. Well, it's got to be the case that having $1 more in hammers will increase output by $1, or else, why buy or make them on the margin, or why not make more? So it'll still be the case that this formula holds. You get the savings by making hammers, more efficiently or something, and you can say, okay, output will increase by as much as if we just had proportionally more hammers. At least, for kind of, yeah, on the margin. A very quick gripe of mine is a little bit petty, and forgive me. But is that, yeah, in that paper from Acemoglu that I was discussing 2 slides ago, he uses what I was calling the first application of the envelope theorem. Okay, this sort of analysis of increases in labor augmenting technology by task. But just because like this stuff is so widely used and it's important, I think it's, it might be helpful to keep an eye on the details here and understand them as well as we can. So, yeah, that's what he basically does. And that's what we can do, because what we have are estimates of increases, not in TFP from LLMs by occupation or by task or whatever, but estimates of the increase in labor augmenting technology, how much labor savings we can get by task, and then aggregating by occupation. So we have the inputs to apply application 1, and he basically does apply application 1. But not quite. Instead, what he does is he does this sort of intermediate step of converting everything into TFP terms, applying Halton's theorem, and converting back. An issue with doing that, though, is that to apply Halton's theorem, we need the Domar weights by, ideally by task, but at least by occupation. But we don't have those. And so he takes each occupation's wage bill as a share of the aggregate wage bill as a proxy for its like total expenditure, like on that occupation, as a fraction of total expenditure. So that would be the Domar weight. So just think for a moment. Is this proxying, taking each job's wage bill as a fraction of the total wage bill as a proxy for the Domar weight, right? Like total spending is a fraction on I as a fraction of Y overall. Is that equivalent to assuming that the capital shares are equivalent across jobs? The answer is yes. Yes. So when applying Halton's theorem, this analysis assumes that the capital shares are equal across the occupations. But to get the increase in TFP for occupation, for occupation little I and industry big I, he uses the industry level labor shares, right? He doesn't just like use the aggregate labor share for the whole economy, right? Which would work if like every occupation had the same labor share. No, he uses the industry labor share. So he's like trying to get at the actual, as close as possible to the actual labor share in that occupation. And that's how you kind of, you convert the estimates of increases in labor augmenting technology to increases in TFP for that occupation. So we've got like this part of it. We've got something close to what we need to apply Hilton's theorem on this part of it. We can sort of convert the BIs into PIs, but we can't do that when computing the Domar weights. So the upshot is just that like trying to convert everything to TFP and back isn't always necessary. In fact, here it is unnecessary. And it's done inconsistently in that paper. When you just compute the predicted proportional increase in output directly using our equation 7, you get a higher estimate of the GDP impact of LLMs than reported in that paper. It's a very, very slightly higher estimate. I mean, nothing hinges on this, but I think it's good to keep an eye on some of the technicalities here because sometimes sometimes they do diverge. All right. Finally, just note a limitation of applying the envelope theorem, including all of its applications, like the Halton theorem, is that it only really holds for small shocks. Okay, it only holds on the margin. There's various work, in particular, Baki and Fari have some work extending Halton's theorem beyond the first order approximation. And when we're considering large shocks, like AI seems like it at least has the potential to be, this can be important. So like the envelope theorem might just not be the right tool to use. As an example of how this could be important, Dan Carey here has a comment on Matthew Barnett's analysis of the GDP impact of fully automating remote work. Barnett assumes a CES production function over remote and non-remote work, and imagines what happens if we can like fully automate the remote work. But of course, even if you estimate the like local impact of automating a bit of remote work, as you can, if you locally know the derivatives here, you locally know the substitutability. That doesn't necessarily tell you what'll happen, far away from the margin when you're automating, 50% of remote work, let alone 100. So Carey's illustration of how this can go wrong is if production consists of like multiple CES nests, then the aggregate elasticity of substitution between R and N will change with how much you've already how much of the R you've already automated, basically. Which sectors you've already taken out of the equation. So the substitutability could be really high for small increases in R, for instance, leading you to think that fully automating remote work would lead to a huge increase in output, but then fall arbitrarily quickly for larger shifts, like automating kinds of remote work that are far from the current margin. I mean, it can go either direction in principle. But yeah, just don't be fooled by the first functional form you write down. I think it's the lesson. CES functions can be good for simplicity, and so can first order approximations, but they can't be applied far out of sample. All right, so to recap, in a Cobb-Douglas task-based model, increasing automatability increases that exponent, that T thing, on capital. And this seems like a bad model of automation, right? Because it implies that automation would increase the capital share and the growth rate, both of which have been remarkably constant over the very long run. By contrast, a gross complements task-based model, along the lines of Aghion et al., for instance, does match the Caldor effects, at least asymptotically. The funny thing is that, as this model also shows, teaching capital new tricks, automating more of the tasks, raises labor augmenting technology rather than capital augmenting technology, and even has this funny effect early in time of being capital depleting in a sense. When evaluating whether capital is complementing or substituting for labor, you can't just look at the micro level data, like the task by task function, and assume that that says something about the macro level impact, right? In the Aghion et al. Model, within each task, the factors are perfect substitutes, at least if you can use capital at all. And yet, it's still the case that in aggregate, because of the the cross task effects, the factors are as complementary as you like. And then finally, the model also showed that you can get Caldor forever, even as we get arbitrarily close to the finish line of full automation, at least if we get there slowly. But if we actually cross the finish line, or if we just approach it quickly enough, then we get an AK economy. And we can get an AK economy under weaker conditions if we have like hard retraining bottlenecks. Finally, all these models have glossed over the possibility of new tasks, but that's remediable without kind of changing the intuitions that these models illustrate, which is why we didn't get into it. But something that's not so straightforwardly remediable is the possibility of like complementarities over who's doing what, whether it's like the same person or the same entity, person or machine, that's writing the email and having the Zoom call. And yeah, when you account for those, I think you might get rather different projections about how automation will unfold, in particular that it'll happen later, but then faster, and maybe be kind of like even more powerful than you would predict in a simple model, because you can have like one machine taking advantage of all these complementarities by sort of doing everything at once. Okay, great. Oh, yes, and then we discussed the envelope theorem and its applications, careful and otherwise.